Good afternoon, friends and neighbors. Hey, isn't it about time we tackled access control lists? So first up, what is an access control list? Well, it's a tool. We use them all over the place. It's a tool for specifying certain kinds of traffic, networks or endpoints, and then we use a mask or a keyword to specify what we call the match criteria. But we're doing this in order to accomplish some goal. And the goal might be to control traffic in a variety of ways. It might be permitting or denying traffic, allowing appropriate access. It might be because we want to rate limit specific traffic or users or devices. And then, of course, we can use it for network address translation. Now, the first thing to realize is that an access control list comes in two parts. And the first part is a container or a list. It's just a collection of rules that we're going to use to specify traffic or applications. And then the second part is we're going to apply that list to something. The most common thing we apply it to is interfaces, but as we'll see here in a little bit, we can apply them to a lot of things. Now the container part, normally what we do is we identify a node or nodes or a particular kind of traffic by IP address or by network. But we can also think of things like applications or people. And a really common example that we might use is 192.168.1.0 to identify a particular network. Now a network mask looks like that, 255.255.255.0. But we'll see here in a little bit that access control lists use a completely different kind of mask. Now once we have our list or our container, we might apply them to interfaces, and we might be controlling traffic, allowing or denying a particular kind of traffic, but we might use them for network address translation in order to determine what's going to be routed or what's going to be translated. We can also use access control lists in conjunction with rate limiting, controlling the amount of traffic through a particular interface, or even classes and policies that specify a particular precedence, priority, or treatment for traffic. Here are some match criteria examples. Now, your filter list or your container has a bunch of things in it. And how do you know whether or not the traffic in question is a match for that list or container? Well, it's because we use something called match criteria. So the match criteria describes what it is that you're trying to control, modify, or administer. In the example on the top, it's something equal to HTTP traffic. Okay, pretty straightforward. The next one is ICMP. But we can get really specific. We can talk about particular hosts. We can talk about networks. And when you have match criteria, the first thing we worry about is, all right, what's the number here? What's the value of the network or the host that we're looking for? And then are we going to permit or deny it? And then later on, we'll see that we're going to use this access list or this match criteria in some way. The last two examples at the bottom there show that we can match on DSCP value, which fills the spot in the IP type of service field. But if you do Wireshark capture or something like that, you'll see that it's now called diffserv code points. What we have to remember is at the end of every container, at the end of every lists of rules, we have something called an implicit deny all. So if you don't permit traffic, it's automatically going to be denied. So let's think a little harder about match criteria. There's a couple things that we have to do when we get a statement like this one here. So we have access list 101 deny, and this particular match criteria is 192.168.1.2 or 1.128, and then the mask is 0.0.0.127. Now don't freak out over the masks. We'll cover them here in a second. But when we want to understand this statement, we have to unpack it in a couple of steps. First thing is, what's the match criteria? Well, the first one is that number. And in this particular case, the match criteria is a set of hosts ranging from 1.128 to 1.255. That's because of the mask that's being used there. Now again, we'll cover masks here in a little bit. Okay, so let's assume that something matched that criteria. If it didn't, you would just go on to the next rule. But if it matches this criteria, now what do we do? Well, it's going to be permitted or denied. Okay, so that's the permission. Great. We've decided that in this case, we're going to deny it. Okay, denied from what? Well, it might be straight up controlling traffic. We're going to put this on an interface in a particular direction, and that traffic is going to be denied. But if it's used in conjunction with network address translation, then the traffic would be routed probably instead of translated. If it's quality of service, this particular traffic or flow might not receive precedence or priority handling. So you can see that it really depends on how the access list is going to be applied that determines what actually ends up happening. So here's some examples of applying the match criteria. So we've got our access list, right? And in this case, we've given them numbers. So you have a list of rules called 101, a list of rules called 102, 10, and 191. Or you give it a name, blah or yuck, whatever it is. And in the first example, it's applied on an interface. So that's very straightforward. This list of rules is applied to traffic coming in or out of this interface. In the example of the network address translation command, if the traffic is in that access list, then it will in fact be translated. The last two are about quality of service. We are going to take anybody that's in that list, 190, 191, and they're going to be given that set of rate limiting boundaries. And in the last case, whatever the treatment is for the class map. So the class map says anybody in this class, this access list is now this particular class. And then later on, we would determine its treatment. So it's really important to realize that access lists are not just for security. Now, before we go any further, let's talk a little bit about these masks. It turns out that in computing, we use masks all the time. File permissions, for example. Change mod 755 would give us the resulting permissions on a file or a directory. And the mask is just a way to indicate what those permissions actually are. In subnetting, of course, we're used to using masks that look like the second example here, 255, 255, 255.0. And we remember that masks are used in that case to identify the network for a particular host. We've got masks in routing protocols like OSPF and EIGRP. And now we're talking about masks in conjunction with access control lists. All right, so to get us started, let's start with a network mask. So a network mask, as we know, is bound by a logical operator. So if we break the IP address out into binary, like on the bottom right, and then we break the mask out into binary, and then we do a bitwise and we do all of the ANDing operations, we would wind up with, in this case, 192.168.1.0. And so 1.46 lives on the 1.0 network. And we know that because we did the ANDing operation, and that's the whole point of a network mask. Now, another way to think about this is the network mask tells us what we care about. And for a network mask, what we care about is where the ones are, the binary ones in the mask. So anything that's got a binary 1 underneath it, in this case, that's what we care about. The rest can be any other value at all, and it just doesn't matter because the things that are important are 192, 168, and 1. Now, network masks or supernetting masks or subnetting masks or CIDR masks, variable length subnets, they all have a couple of rules. One is that they're powers of 2. And by that I mean that the address space is a power of 2. When I start subnetting, I break network spaces up into 2. So if I subnet again, I've broken it up into 4. If I steal another bit, I've broken it up into 8. I steal another bit, I've broken it up into 16 chunks of address space. They're all powers of 2. So it not only is it powers of 2 for 2 networks, 4 networks, 8 networks, 16, but also the number of hosts in that particular address space is also based on a power of 2. So we see 128, then 64, and 32. All of those are powers of 2. Now, I've done an example here of where I just started slicing up the network space, and the reason that I did that is because no matter what you do with the slicing, the addresses have to be continuous. So 0 to 255, well, I cut that in half, it's 0 to 127. I cut that in half again with that match criteria, it's 0 to 63, 0 to 31, and so on. When I start putting them back together again, I start putting together continuous address space. That's really important. If I start doing it in the supernetting direction, I put together 2 Class Cs, for example, 4 Class Cs, 8 Class Cs, and all of them will be in a continuous address space. You don't get to take a chunk from over here and a chunk from over there and put those together. That's not the way it works. It's all going to be continuous address space and all based on powers of 2. And we see similar numbers being used all the time. So the numbers in the bottom right in this little table, if I steal bits from the network portion, I know that I'm going to be seeing numbers 255, 254, 252, 248. If I steal them in the other direction, I'm going to be seeing 128, 192, 224, 240. Always. It's always the same way. So there are a couple of limitations for network masks. For ACLs, we use wildcard or inverse masks. Wildcard masks, they work a little bit differently, although at a glance, they seem like they're just the opposite. So if you take a network mask for a particular network, in this case, 192.168.1.0 would have a network mask of 255, 255, 255.0. And we do the inverse, we just flip the bits, we would wind up with a wildcard mask, 0.0.0.255. Both of them would correspond to a range of addresses, 192.168.1.0 to 1.255. But in this case, the logical operator is OR, and we'll see why that is here in a second. So let's do a little bit more detailed example, or a little tougher example. If we have the address space below, 192.168.1.254, that's the network, and then we have a mask corresponding 255, 255, 255.224. What we wind up with is an ANDing operation that looks like that. And the ANDing operation would result in the same value no matter what we put in the host portion indicated by all zeros. Because when you AND anything with a 0, you get a 0. The corresponding wildcard mask would be 0.0.0.31, because if you take that same network mask and you flip all the bits, that's what you would get. Now, if we take the last octet and we split out the binary for the network portion and then we split out the binary for the mask, it would look like that. And then if we did the OR operation, we would get that funny value down there at the bottom of all ones. But the important thing to remember here is that in the wildcard mask, zeros show us the things that we care about. Where before we said network masks show us or give us ones to indicate what we care about, now we're going to use zeros. And so that means that where the ones are, it doesn't matter what you put in there. Because if it's a 0 or a 1, I'm going to give you the same exact result. It just doesn't matter. Okay, so the zeros show us what we want, and the other bits, the bits that are not part of the mask, the bits that have ones underneath them, can be a 0 or a 1. Well, let's take another look at that. Okay, so the reason in a network mask that the range in this particular example is 224 to 255 in the last octet is because we ANDed with zeros, and anything ANDed with a 0 gives us a 0. So it doesn't matter what you put in the last 5 bits, because as you can see, the red portion there, those are all zeros. And so in the zeros above, if you put any pattern in there, no matter what, when you AND them with those 5 zeros, you're going to get zeros. So it's always going to be 224 in the network address space. The reason that the wildcard range is also 224 to 255 is because the only thing we care about are those first 3 binary positions indicated by the zeros. And up above that, we see those first 3 ones. So the match criteria are those 3 ones. And the mask says, those are the ones that I really care about. All the other ones that are above the red ones, I don't care. You can put a 0 or a 1 there because I don't care. So the last 5 bits could be zeros or ones, and that would give us a range of 111, and then all zeros, to 111, and then all ones. And it just doesn't matter because the result is exactly the same. Okay, so network masks use ones to indicate what we care about and zeros for what we don't care about. Wildcard masks use zeros to show us what we care about and ones to show us what we don't care about. And they have this really strange looking mask, and I'm not really sure. So why in the world would we use wildcard masks? Why don't we just use network masks everywhere? Well, it turns out that wildcard masks are a lot more flexible than subnet or supernet masking. For one thing, the address space doesn't have to be continuous. You can use almost any value you want in a wildcard mask. That's why they're called wildcards. So you can target one host, you can target a variety of hosts, you can target patterns like odd or even hosts, and I've got a couple of examples for you down below. So we don't have anywhere near the level of restriction that we do with network masks. So let's take the example of a host 10.11.12.13. If I put all zeros in the network mask, in the wildcard mask, then the match criteria now is just that particular host. Because what we've said is it's all zeros. 32 bits of all zeros. So that means that I care about everything in the host portion. If I take that same address, 10.11.12.13, and I change the wildcard mask to 0.0.0.1, then the match criteria just changed. And the reason it just changed is because I've just said I don't care what's in the very last bit. It can be a 0 or a 1. That means that the match will be 10.11.12.12 or 10.11.12.13. Because if I don't care about that last bit, the binary patterns are the same. But what about 14? Well, it turns out that 14 does change the binary pattern of the bits that I care about. And so 14 doesn't count. But what happens if I change the wildcard mask again? 10.11.12.13, but this time the wildcard mask is 255, 255, 255, 255. That means that I've just said I don't care about any of these bits. So in that case, it matches any host at all. If I change it again to 0.255, 255, 255, that means that the address can be anything. The match criteria can be anything as long as it's on the 10net. Now here's one that's kind of for fun on the bottom there. Let's change the mask and change the match criteria, the prefix there. It's now 10.11.12.0 and the mask is 0.0.0.254. I think that's right. 0.0.0.254. So take a look at the last octet for both portions. All zeros and then all ones except for the last bit is a 0. This means that we're looking for even numbers on the 10.11.12.0 network because the last bit has to be a 0 and that's where we get our even numbers from. So that's what we mean when we say that wildcard masks are a lot more flexible. You can do a lot of crazy things with a wildcard mask. So let's talk about a couple of ways to build access lists. There are a lot more than these, but we're going to cover standard and extended. The difference between standard and extended access lists really come down to adding a little bit more complexity. So standard access lists numbered 1 to 99 usually are testing on source criteria. So you permit or deny based on the host criteria, and then of course they accumulate. You can have lots of rules. And don't forget the implicit deny all at the end. But now if we take a look at extended access lists, numbered 1 to 199, we've got lots more fields. So we can test on source and destination, port numbers, all kinds of things. So lots more complexity. We also have keywords such as host or any. So if you use the keyword host, it's the same as saying a particular IP address, and any means just what it sounds like. Here are some standard and extended access list examples. In both cases, the first thing you're going to do is create and then apply them. So in this case, we've got access list 3 deny, access list 3 permit, and then we go down to an interface and we're going to apply the particular access list to an interface and a direction. And the extended access list is much the same thing. We create the rules and then we apply the filter list to a particular interface and a direction. Now let's take another look at applying the criteria. In those previous examples, we were applying them to an interface and direction, so very much about traffic control, permitting or denying traffic. But we can also apply them to network address translation commands, right? And that doesn't have anything to do with controlling traffic as far as permitting or denying it on a network. Here we're deciding, well, do we translate it or do we route it? If we're using them in quality of service commands like rate limiting or policies, well, then we're applying a particular treatment. We're rate limiting it. We're saying we're going to provide priority or precedence handling for a particular kind of traffic. So it's not about stopping it or allowing it through. Well, thanks for watching. Thanks for listening. This has been a look into access control lists and masks. Next up, we'll take a look at some of the other important ideas associated with ACLs, and we'll talk a little bit more about that in and out of direction sort of thing. Like and subscribe if I helped, and until next time, may your packets always reach their destination.